Hey friends, in this video we'll go over 9 practice problems to help you master the differences between SN1, SN2, E1, and E2 reactions. Now feel free to pause the video so you can try these on your own before we go over them together, and don't forget you can download the PDF in the description along with the other resources that we'll be using in the video. Now before we dive into the first question, I do want to go over the flowchart that I'll be using throughout the entire problem set, and this is the thought process I use whenever I'm trying to decide on if I'm going to have an SN2, SN1, E2, or E1 reaction. So the first thing I look at is I try and decide if I have a strong or weak base or nucleophile. Now if I do have a strong base or nucleophile, then that is going to tell me that I'll be going down either the SN2 or the E2 route. And in terms of which reaction I would use between those two, it all depends on both which leaving group I have, and then also if I'm presented with a nucleophile or a base. So as we keep on going throughout this problem set, we'll be able to see which reaction is which. And then in terms of us having a weak base or nuke, that'll be telling us that we have either an SM1 reaction or an E1 reaction. And then we'll also be looking at the leaving group and other reagents and reaction conditions that we have as well. So starting off with our first example, the first thing I'm noticing is that we have a weak nucleophile or base. So if you can remember from that flowchart, we are presented with a weak base or nucleophile that is telling us we'll be going either down the SN1 or the E1 route. And the next thing I'm going to look at is where is our leaving group. We can see that our leaving group is going to be right here on that secondary carbon. And since we have a weak nucleophile along with a secondary leaving group, that is telling me that this reaction will be SN1. And the reason it's SN1 as opposed to E1 is just because for those elimination reactions in terms of E1, we are usually presented with heat. And in this example, we do not have heat. So if we were to go through the mechanism, our leaving group will go ahead and leave, the electrons will fall back onto that bromine. And in doing so, we then create a secondary carbocation. But one of the things we always have to watch out for whenever we do form a carbocation is if a carbocation shift can occur. Now, one of the things I'm noticing is that left of the leaving group, right here, we do have a tertiary carbon. And in terms of carbocations are usually the most stable whenever they are on a tertiary carbon. So what we'll see happen is that the electrons between that carbon-hydrogen bond will actually shift over towards that secondary carbocation. And because of that shift, which is what we call a hydride shift, we are actually placing that carbocation on a more stable tertiary position. So now that we have our carbocation on the tertiary position, we also have to remember that we have ethanol floating around in our solution as well. And if you can remember from earlier, that ethanol, the lone pairs on the oxygen, is going to act as our nucleophile. So we'll see the lone pairs of the oxygen go and attack that carbocation. And in doing so, we then create a new carbon-oxygen bond. So in this reaction, we can see that we formed that new carbon-oxygen bond. And since oxygen has that positive charge, it is then making this hydrogen more acidic. So what we'll see from here will be an acid-base workup step, where we'll have another ethanol molecule act as a base, and the lone pairs will go and steal that acidic hydrogen, the electrons fall back down onto oxygen, and then in doing so, it has then neutralized that oxygen, and we'll then have our final product. So I'll go ahead and zoom out of this example so you can see the entire mechanism. And just to reiterate, this was an SN1 reaction. Now for our second example, yet again, we'll look at what is above our reaction arrow. We can see that we have sodium hydroxide. Now since we do have a hydroxide, that means we do have a strong base. And since we do have that strong base, one of the first things I will go ahead and do is look at our starting material and see if there is an acidic hydrogen. Now, whenever I do have a strong base, I always check on the starting material to see if we do have an acidic hydrogen, just because whenever students see this negative charge and a good leaving group, students will get reaction happy and just assume that they can attack the electrophilic carbon immediately, but you have to remember that acid-base reactions always happen first. So if we do look at our starting material more closely, we can see that we have an acidic hydrogen right here, and that will be the first step of the reaction. So step 1 will be an acid-base reaction, where the lone pairs of the oxygen will steal the acidic hydrogen, then the electrons will fall back down onto oxygen. I'll go ahead and draw out the product for you guys. And now because of that acid-base step, what we ended up doing is we gave this oxygen a negative charge, therefore turning it into a better nucleophile. And since we have this nucleophilic oxygen on the same molecule with our good bromine leaving group, what we'll observe is an intramolecular SN2 attack. So what that means is that the lone pairs on the oxygen will actually attack the electrophilic carbon on the same molecule, which will then kick the bromine out as a leaving group. But here's where it gets tricky. A lot of students will get tripped up in terms of how to draw this structure, and this is where counting will help you out a lot. So whenever I'm presented with an intramolecular attack, the first thing I always do is I start counting at my nucleophile, and then I stop counting at my electrophile. So we'll count with the oxygen first. We have 1, 2, 3, 4, 5 right there. And since I counted 5, my structure will look very similar to a cyclopentane. But the only difference is that oxygen is actually going to be at the center of that structure. So we have our oxygen at the center. But before I complete the bond between carbon and oxygen, we have to remember that because we did have an SN2 reaction, inversion of configuration always occurs during those SN2 reactions. So since our bond right here was wedged, that means in our product, because of inversion of configuration, we will now have a dashed bond. Now, one thing we can't forget about our product is that we still have a substituent that we need to include. That substituent will be right here, which is just one of our methyls. And usually whenever I do have to draw one of these products that happen because of an intramolecular attack, I always go through and count my carbons just to make sure I have all of them. So if we were to count the carbons on this molecule right here, we have 1, 2, 3, 4, 5 carbons in total. And then for our product, if we were to check, we have 1, 2, 3, 4, 5 carbons as well. And yet again, just to reiterate, this bond between the carbon and oxygen is dashed only because inversion of configuration occurred between this nucleophilic attack with that wedged bromine. So I'll go ahead, zoom out, and show you guys the mechanism. And then just to reiterate, this reaction was an SN2 reaction. Now for the third example, the one thing that is really catching my eye is the heat that we have as one of our reaction conditions. So whenever you do have heat as one of your reaction conditions, I immediately want you to think E1. And one of the ways you can make sure that it is E1 is you can also check and make sure that you have a weak base, which water in this case will act as our weak base. So we'll go ahead and write down E1 for this reaction, and now we'll go over the mechanism. So if we were to look at our starting material, we can see that we have a really good tertiary leaving group. So our leaving group will go ahead and leave. The electrons will fall back onto the iodide. And in doing so, we then create a tertiary carbocation. And like I said earlier in this example, we'll be undergoing an E1 reaction, just because we do have that heat in the reaction conditions. So our water is going to act as a base and will be stealing a hydrogen. But the main question is, which hydrogen are we going to steal? Our two main options, which will have the most substituents for our new alkene, is we can steal a hydrogen on the left side of the carbocation, or we can steal a hydrogen on the right side of the carbocation. Now, whenever you are presented with a reaction like this, where you can either steal one hydrogen or the other for E1 reactions, I always want you to ask yourself, which reaction is going to make the most stable alkene? And in this case, the most stable alkene is going to be the most substituted. So if we were to steal this hydrogen over here on the left, that means we'll be forming a double bond between these two carbons. And if we did form a double bond there, we would have 1, 2, 3 substituents. But if we were to steal the rightmost hydrogen and form a double bond between these two carbons, that would mean we'd have 1, 2, 3, 4 substituents. So since the rightmost hydrogen will give us 4 substituents for our alkene, as opposed to the leftmost hydrogen only giving us 3 substituents, that means we're going to steal the rightmost hydrogen. So the lone pair on the water will steal that hydrogen, and then the electrons between that carbon-hydrogen bond will then drop on down to form our new carbon-carbon double bond. And right there is going to be our final product. As you can see, yet again, our double bond has 1, 2, 3, 4 substituents. I'll go ahead and zoom out so you guys can view the full mechanism. So for our fourth example, if we look above the reaction arrows yet again, we see that we have a strong base. And since we have a strong base, which is a hydroxide, the next thing I want to look at is what is our leaving group. Right here is our leaving group, which is bromine, which is pretty good. We can see that it is a secondary leaving group. So since we have a strong base and a secondary leaving group, that is telling me it's either going to be E2 or SN2. And one of the things I want you to keep in mind is that whenever you have a molecule that can act as a strong base and a strong nucleophile, is that if it's ever given the chance to act as a base first, it will, just because acid-base reactions, if you can remember, happen a lot faster. So in this case, we'll be undergoing an E2 reaction. And one of the main things about E2 reactions is that your leaving group needs an anti-periplanar hydrogen. So if we were to zoom in and look at the example, I went ahead and drew in the additional hydrogens of the molecule up here. And just to reiterate, the reason this hydrogen is wedged is because our methyl group is dashed. And then over here, since our methyl group is in the wedged position, that is forcing the hydrogen to be in the dashed position. Now, if you can remember, anti-periplanar hydrogens just means that the hydrogen is going to be 180 degrees apart from our leaving group. And in terms of the wedged and dashed bonds, that is telling us that the notations have to be different. So for example, in this case, the right side is going to have our anti-periplanar hydrogen just because our leaving group is currently wedged while our hydrogen is dashed. But over here on the left side, our hydrogen is not anti-periplanar because our leaving group is wedged, and this hydrogen as well is also wedged. So I'll go ahead and show you the mechanism of the lone pairs on our hydroxide stealing the hydrogen, and then the electrons between that carbon-hydrogen bond are then going to fall down to form a new carbon-carbon double bond between these two carbons right here. And as those electrons are falling down to form that new double bond, our leaving group will then be kicked out. And that'll leave us with our final product. And one thing I will note is that the stereochemistry on this methyl group over here on the left side will not change just because we did not react with our carbon right there. Now for our fifth example, we have to decide on if this molecule is either a weak or strong nucleophile. Now at first glance, you may tell yourself that it's going to be a weak nucleophile just because there is no charge, but unfortunately, this is where memorization kind of starts to come into play. So in the description, like I said at the beginning of the video, this is included in the PDF that you guys can download, and this is a nice little chart that kind of showcases the common weak and strong nucleophile or bases. So one thing I will note is not all strong nucleophiles are also strong bases, but all strong bases are strong nucleophiles. So it may be a little confusing at first, so here is a good chart to kind of help you gauge between which is which. And if we were to look at the bottom left-hand corner, we have our list of strong nucleophiles only. And we can see that phosphine actually makes it onto the list of being a strong nucleophile. So yet again, feel free to download this PDF, but we'll go back to our example. So now that we know that phosphine is actually a strong nucleophile only, the next thing we'll be looking at is our leaving group. And right here, we can see that we have a secondary leaving group. And this right here is deuterium, which is an isotope of hydrogen. And we'll treat that like it's a regular hydrogen, but the stereochemistry will be important throughout the reaction. And since we have a strong nucleophile only, along with a good leaving group on a secondary carbon, that is telling us that we're undergoing an SN2 reaction. Now earlier, when we had a hydroxide along with a secondary leaving group, we actually had an E2 reaction only because the hydroxide can act as both a strong base and a strong nucleophile. But in this example, phosphine only acts as a strong nucleophile. Now, pro tip, the reason that we have strong nucleophiles only, as opposed to strong nucleophiles and strong bases, is because strong nucleophiles usually has a factor of stability such as size or resonance or something along those lines. And in this case, the factor of stability is that phosphorus is a really large atom, so it's a lot more polarizable in terms of the lone pairs. So we'll go ahead and treat this like any standard SN2 reaction, where the lone pairs on our nucleophile will go and attack our electrophilic carbon, and in doing so, it will then kick our leaving group out. And since we are undergoing SN2, the one thing you have to be aware of yet again is inversion of configuration. Now, since our leaving group was in the wedge notation, inversion of configuration is telling us that the carbon-phosphorus bond that we just formed is actually going to be in the dashed position. And like I was mentioning earlier, the deuterium, we do have to represent the stereochemistry as well. And since it started off in the dash position, inversion of configuration is telling us that it's going to be in the wedge position. Now, one thing I will mention is that since our final product does have a positive charge, our bromine that actually left in the reaction, since it does have a negative charge, will interact with the molecule to help stabilize the positive charge. So I'll go ahead and zoom out so you guys can see the mechanism. And yet again, this was an SN2 reaction. Now for example 6, it is a little tricky just because there will be a carbocation rearrangement. But to start off our reaction, we first have to look at what is above the reaction arrows. We can see that we have methanol, which will be acting as our weak nucleophile. And then we can also see that we have a secondary leaving group. So we'll go ahead and showcase the mechanism. So step 1 in this reaction is our leaving group will go ahead and leave. And in doing so, we then create a carbocation. And since we have the secondary carbocation, a good rule of thumb is that whenever you do form a secondary carbocation, is to always make sure that you can or can't undergo a carbocation rearrangement. So if we were to look at the right side of the carbocation, we can see that we have a primary carbon, which would not be an ideal place to put a carbocation. But if we look over at the left side of the molecule, we can see that we have this double bond right here. So in this molecule, we'll see that the electrons between this carbon-carbon double bond will want to be delocalized because of resonance, and will want to move towards that carbocation. And since they are moving towards that carbocation, it is spreading the positive charge throughout the molecule. And because of that, we will then see that there is also a partial positive charge on this tertiary carbon as well. We can see that the carbocation is now in that tertiary carbon, which is placing it in a more stable position. Now don't forget, we still have our methanol in the solution, and the lone pairs on that oxygen will actually go and attack our new carbocation that's in the tertiary position. And because of that, we are now forming a new carbon-oxygen bond. And don't forget, while you do have that reaction, you still have to include the double bond that we had because of resonance. And since we still have a positive charge on this oxygen, it is making this hydrogen right here acidic. So we'll undergo an acid-base workup step with another methanol that we have left over in the solution, where the electrons on the oxygen will steal that acidic hydrogen, the electrons fall back down into oxygen, and then we have our final product. And just to recap with this example, we underwent an SN1 reaction. And one thing to note as well in terms of why carbocation rearrangements are so important is because if you look at the start of the reaction, we have our nucleophile and our leaving group right here on that secondary carbon. At first glance, it looks like our nucleophile will attack that secondary leaving group and that our reaction center will be on this carbon. But when you undergo that carbocation rearrangement, we actually see that our reaction site is actually this carbon right here. So this example is a good example as to why showing those carbocation rearrangements are so important. So for our seventh example, above the reaction arrows, we see that we have this really large molecule, and on that large molecule, we do have a negative charge on that oxygen. And the reason we know we have that negative charge on the oxygen is just because that potassium has that positive charge. And since we have a negatively charged oxygen, that is telling us that we have a strong base. But our strong base, if we were to look at the rest of the molecule, has all these large substituents, which makes this a bulky base. Now, whenever I'm presented with a strong, bulky base, the first thing I'm thinking of is an E2 reaction. But just to make sure, we'll also look at our leaving group as well. And by looking at it, we can see that we have a tertiary leaving group. One thing to note about tertiary leaving groups is that they will be unable to undergo SN2 just because there would be too much steric hindrance whenever the nucleophile would undergo backside attack. So since we have a big bulky base along with a tertiary leaving group, that is telling me an E2 reaction will occur. But one of the things we have to look out for E2 reactions whenever we do have a bulky base is the type of alkene we'll be forming. Now when it comes to alkenes, you can either form the Zaitsev alkene, which is the most substituted, or you can form the Hofmann alkene, which is going to be less substituted. And since we have a big bulky base, there's going to be some steric effects. And since there are steric effects, we are forced to form the Hofmann alkene. So instead of stealing a hydrogen that would be all the way out here to form a carbon-carbon double bond between these two carbons, which would form a Zaitsev alkene, we'll have to steal the outermost hydrogen just to reduce those steric effects. So we'll have the lone pairs on our bulky base go and steal that hydrogen. The electrons between that carbon-hydrogen bond will then fall on down to form our new carbon-carbon double bond. And then our leaving group at the same time will then be kicked out. And from there, we now have our final product, which is also going to include the Hofmann alkene, which we can see right here, which has the least substitution possible. Now, one thing I will note about this E2 reaction is that if you can remember from our previous E2 reaction, is that we were worried about an anti-periplanar hydrogen. So right here is our leaving group, and if you can remember, the hydrogen must be anti-periplanar in order for the leaving group to leave. And the reason we weren't worried about it in this example is because this carbon right here is bonded to 3 hydrogens, so no matter what, there will always be an anti-periplanar for our leaving group over here. Now on to our 8th example. If we look above the reaction arrows, we can see that we have a weak nucleophile. And your first instinct may be that this is going to be an SN1 reaction, but this is where the leaving group and the rest of the molecule comes into play. So if we looked at our reactant, we can see that we have a primary leaving group, but then if we were to look at this functional group right here, we also see that we have a strong nucleophile on the same molecule. Now this is where some memorization may need to come into play yet again, just because as you first look at that nitrogen, there is no negative charge, so at first glance, it doesn't really stand out as a strong nucleophile, but this is one of the really strong nucleophiles you need to know, just because it is an easy question that professors may use to try to trip you up. Now, one thing I will note is that if you ever see ammonia like that, that is not a strong nucleophile. I just wanted to point that out for you guys. So since we have a strong nucleophile on the same molecule as a good leaving group, we can actually ignore the methanol over there and kind of treat it as a solvent. And one thing I will note is that this is a polar protic solvent, which in terms of SN2 reactions, which this is right here, polar protic solvents aren't favored. But since our strong nucleophile is on the same molecule as our good leaving group, it really won't matter that much just because of the proximity of both the nucleophile and the leaving group. So we'll go through this together, where the lone pairs on our nitrogen will act as our nucleophile, we'll go over and attack our electrophilic carbon, and then the electrons will fall back onto bromine. And in terms of drawing this structure, yet again, we'll always want to count from our nucleophile all the way down towards our electrophilic carbon. So we have 1, 2, 3, 4, 5. Now, just like the reaction from earlier, since we did count 5, it will resemble a structure similar to cyclopentane, but with our nitrogen at the center. So we'll have nitrogen, and we can't forget the 2 hydrogens. And our nitrogen will have that positive charge. And since our molecule has a positive charge overall, that bromide is still there floating around, so the negative charge on the bromide will come over to help stabilize the positive charge on our molecule. So yet again, just to reiterate, this was an intramolecular SN2 reaction just because we had a strong nucleophile on the same molecule as our good leaving group. Now for our final practice problem, yet again, we'll look at what is above the reaction arrows. We can see that we have a weak nucleophile with ethanol. But now if we were to look at our reactant, we actually see that we have 2 possible leaving groups. We have a carbon-bromine bond, and we also have a carbon-fluorine bond. So in this question, you have to ask yourself which leaving group will be the best out of the 2. And pro tip, whenever you have fluorine as a quote-unquote leaving group, it's actually a really awful leaving group, so you can always ignore that. So since fluorine is a really poor leaving group, we'll only be focusing on our bromine. So we'll go through the mechanism together. The bromine will go ahead and leave as our leaving group. And in doing so, we then create a secondary carbocation. And the stereochemistry of our other substituents has yet to change because we have not reacted with them yet. But in terms of this stereocenter, we are now going to interact with it just because a hydride shift will yet again occur. Because as you can remember with our rule of thumb, whenever you have that secondary carbocation, always check for possible carbocation rearrangements. So over here on the left, we have another secondary carbon, but over here on the right, we have that tertiary carbon, which means that carbocation can be in a more stable position. So we'll undergo a hydride shift where the electrons between that carbon-hydrogen bond will shift over towards that secondary carbocation to help form a more stable tertiary carbocation. And now a couple of things to note for this step. As we can see, yet again, I did not change the stereochemistry between that carbon-fluorine bond, but one of the stereochemistries I did end up changing is the stereochemistry of the methyl. So as we can see in this step, the methyl group was actually in the dash position, but in the intermediate right here, we actually got rid of the stereochemistry, is because whenever you form that carbocation, you actually lose the stereochemistry because the molecule in terms of that carbon is now planar. And since we have our carbocation, we still have our ethanol floating around in the solution, which is yet again our weak nucleophile. So the lone pair on the oxygen will come and attack that carbocation. And in doing so, we have then created a new carbon-oxygen bond. And yet again, that oxygen is still going to have a positive charge, making this hydrogen more acidic. So we'll undergo an acid-base workup step where another ethanol molecule will act as our base, lone pairs will steal the acidic hydrogen, electrons will fall back down onto oxygen, and we now have our final product. So one of the things I will note about this reaction is that if we were to compare the stereochemistry from our starting material to our final product, we can see that we got rid of the stereochemistry on the methyl groups only because we had to form a carbocation on that carbon, but we actually maintained the stereochemistry of the fluorine just because we never interacted with that specific stereocenter. And just to reiterate, this was an SN1 reaction. So I'll zoom out so you guys can see the full mechanism. And by completing this example, that concludes this problem set. And if you have any additional questions about this problem set that we went over together, or any other questions, feel free to comment and I would love to help you out.